Hello and welcome to SETI Live. I'm your host, Beth Johnson, Communications Specialist here at the SETI Institute. Thank you to our viewers from around the world for joining us today. Please let us know where you are watching from. And also welcome in to listeners on the podcast version of SETI Live, which is now available on most podcast platforms. Today, we're going to talk about a new mission. A team of scientists and engineers from the SETI Institute, Impossible Sensing, NASA JPL, and several other institutions will soon test their innovative robotic laser system on a deep sea expedition aboard the EV Nautilus. The mission aims to advance technologies to explore, characterize, and sample the seabed here on Earth. Joining me today is research scientist and project lead Pablo Sobron. Thank you for being here today, Pablo.
Hi, Beth. Pleasure being here.
So tell us, what is this mission? It's called InVADER. What does that stand for and what does it do?
Yeah, so InVADER is a project that started many years ago, and it stands for In-situ Vent Analysis Divebot for Exobiology Research. It's a mouthful, but in essence, what this is, Beth and everybody who's watching today, is the very first time that we bring laser technology to explore the seafloor on Earth as we prepare to explore the oceans of the moons of Jupiter and Saturn, where we know there is water, liquid water, much like we will have here, and there may be life. So we started this project with NASA a few years ago to explore these events, these chimneys in the seafloor on Earth, which may have been the origin of life in our planet. So we're using this as a test bed to prepare for alien ocean exploration in future.
So what are the goals of this mission in general?
So the goals here are to demonstrate a new way to look at the bottom of the ocean. Typically, what ocean scientists do is they bring robots to the seafloor, all the way down to the depths in the Mariana Trenches to 11 kilometers down. They pick samples, they ship them topside, and then when they go to port, they send them to other labs and they analyze them with lab equipment. So as you can imagine, this process involves a lot of people, a lot of boats, a lot of robots, a lot of money. So the goals of this project is to demonstrate that we can do most of that. We're not going to replace that, but we can do most of those analyses in situ. Hence, the in InVADER is the in situ lab. We bring the lab to the seafloor for the first time. So the goal of this particular mission, where we are going next week, is to test for the very first time these new laser ways to explore biology, explore for geology, and essentially have a new set of eyes in the bottom of the sea that can allow us to explore the ocean much faster and cheaper than ever before.
So how does this mission improve upon prior technology to do these things much faster and more efficiently?
Yeah, so the big improvement here is in the speed at which we can gather data and, more importantly, interpret data. So the state of the art, as I explained, still consists in sampling and shipping to a lab and waiting weeks, months to get a result. There are, of course, in situ technologies that scientists have been building for the last half a century that are slowly analyzing water, analyzing chemicals, analyzing rocks there, but they're mostly based on machine vision. Think about your cell phone camera on steroids. Bring it down, and you're taking high-resolution videos and images, and you can start doing very important science just with imaging. But it's not enough. It's very hard to really classify the chemistry, the elements, the minerals, just by looking at them. Ask a geologist, right? So geologists can go in the field and look at a rock. They bring the loop, right? They go close up, and they can tell more or less. But at the end of the day, you need a laboratory of some sorts to really understand that. So I think that what we bring as an innovation, as a almost game changer technology, is this ability to now do what we do in the lab in situ, not just in situ. We're doing this remotely in the field, right? So now think about satellites, right, on Earth, looking down into the ground from up in the sky, and they're using tools to really learn from a distance, right? We're doing the same in the deep sea, of course, we're not doing this at hundreds of kilometers away, but we're doing this at a few meters from the seafloor, right? So the second advantage here is that we don't have to touch. We do not have to sample anything. We don't have to destroy and to interact with the sample itself. We can do all this non-touch, mowing the lawn if you want, on-the-fly scientific discovery from a vehicle, from a robot, without having to stop or collect samples. And that is the fundamental transformation here that we bring, is that ability to do on-the-fly as you drive science with a laser remotely from a vehicle.
That is really interesting, because I have actually done a research trip, and so I've done the whole send the remote vehicle down, pick up rocks, bring them back up, and it's time consuming. And of course, once we get the rocks up, then you have to like sort them, organize them, and then catalog them, and then you take them back to shore and start doing all of the analysis. So what you're saying here is that all gets skipped, and it's basically, here's some lasers, now I can tell you what this rock is right here, what it's composed of. We don't have to wait the trip back to shore, the amount of time to get everything. That is a massive game changer, and I want to talk to you some more about that. But I'm gonna welcome in some people from around the world, it looks like. So we have people watching from New Jersey, the UK, from Wales, Germany, let's see, Latvia, wow, Florida, Mississippi. Thank you. Please continue to let us know where you're watching from. That's awesome. I'm so glad that you're watching from a whole bunch of places. So you've now taken what was a multi-month to year process, and you're going to narrow it down to almost instantaneous. What tools are you using to do that? So you've got lasers. So what sort of analysis can you do in situ on the seafloor?
Yeah, so there is two fundamental techniques that we use here, and without going into the nerdiness of the science of that, we're using light, right? Laser is essentially and fundamentally light, and what happens when you shine light into a rock or a organic mat, right? A coral, perhaps. What happens is that a lot of the light that you shine with is going to come back to you reflected, like a mirror. So no difference between what you shoot at with a laser wise, what you get back. But some photons, once in a while, will interact with the molecules of your rock, of the water around the rock, of the biomolecule that is there on the fluid of the chimney. Some of these photons will interact with those, with the matter, and they will get back to you, shifted a little bit, different energy, which means different color. So if we shoot with a green laser, like we do here, some of these photons are going to come back to us red or blue or yellow, everywhere in between, right? And so the key and the secret here is to measure the difference, right, between the color that you get back and the color that you come in with. So our job is to be very precise on the color that we shoot in. So we have a laser that is very, very, we call it coherent. That means that the color is very pure color. It's only one color, only one shade of green, only that one. We know it very well. And then the second part of the job is to be very good at measuring the colors that come back to you, right? So for that, we have a very innovative camera, if you want, that can really analyze all the light that is coming back to us, all that light that has been shifted by the molecules in the sample. And looking at these shifts, we can really, really start doing fingerprinting of the chemicals that are in this sample. And again, this could be gases, liquids, solids, doesn't really matter. What matters is that this difference in energy, in color of the photons, tells us exactly what the sample is made of and how much of these chemicals are there. So that is the real advancement here, is that we're not essentially bringing the biochemist to the seafloor, right? We're bringing the geologist that can actually tell immediately in real time, using some machine learning, of course, and some advanced technology, to really on the fly, on the instrument itself, to really, really classify the molecules, the elements that are, or how much of each one do we have there.
Okay, I'm still kind of blown away. This is really neat. Why is this type of research important? What, I know a lot of people are probably like, well, this is kind of cool, but what does it have to do with sort of that goal of searching for life? Why the deep sea floor? What are we hoping to get here?
Well, so there's a lot of things.
Oh. We have lost Pablo. He was having some connection issues, and we seem to have had some more connection issues. Hang in there. I'll welcome in some people while we wait. Let's see, we've had a few more. Let's see, from Canada, Sweden, Florida, more Florida, Luxembourg, welcome in. I know that's a friend of mine from Georgia, from Peru, Spain. Oh, from Impossible Sensing Headquarters, welcome. Thank you for watching today. That is Sweden, I believe. Michigan, more Germany. Thank you so much, everybody, for watching. Hopefully, we can get Pablo back in a moment. He should be back in just a second. So what we're talking about is this new mission, which is called InVADER. I know we've put out the links to the press release we just put out today. So this is using remote sensing on the deep sea floor and is making it possible to do sort of in situ analysis of rocks and gas and liquids. And Pablo is back, and now I don't have to sit here and cover time. So, okay, welcome back, Pablo.
Yeah, thanks, Beth, for covering for me. And I apologize, everybody. I'm in the basement here at the university, and as we're finishing the last touches of the instrument before we sail on Monday. And I think the connection is a little finicky, but thanks for the patience. So, as I was saying before I got cut off, the ocean, is the biggest resource we have on Earth to do multiple things. We can use it to feed the world with seaweed farming. We can use it to capture carbon and store it there for millennia, so that to reduce atmospheric load in the environment and reduce global warming. We can use it to, of course, mine minerals that we need to electrify faster. But we can also use it as a window in time to when life may have emerged in our planet. So if you think about all this combined impact of this research can have in the ocean, it really was a no-brainer for me personally to tackle these problems at once. For all the agencies that are supporting this program, including NASA, NOAA, the Bureau of Ocean Energy Management, NSF, and others. And fundamentally, Beth, the thing that I will get out of this personally, and I think scientifically, is that we don't really know how life started, and we almost don't even know when. But there is a good reason to believe that life on Earth emerged in the deep sea, in the deep ocean, in these features that we call the hydrothermal vents or chimneys, small volcanoes, if you want, which have this immense amount of energy stored in it. Think about the ocean, super cold, right? Almost freezing. Suddenly you come in with a fluid that is at 400 degrees Celsius, rich of iron, nutrients, and life loves that stuff, right? Life likes to play at the extremes on this disequilibria, hot, cold, rich, poor, chemical, non-chemical. And we think that metabolic activity started perhaps there. So for us, going there is a window in time on the ability to explore where we come from on Earth. And as a SETI Institute scientist, and you as well and our colleagues at SETI, we're always looking at answering the question, are we alone? And what is the fate of life in the universe? So I think for us, being able to learn more about origin of life on Earth, in future finding life 2.0 on Europa, Enceladus, other oceans out there, is a really fundamental question that is driving all the technology development. But let's not forget that, we're still humans. We're in, spaceship Earth, right? And we have to really be stewards for our planet. So I think that dual application of our technology, not just for the curiosity, if you want, of life, but for the climate impact that this can have in multiple dimensions, like I mentioned, and being able to capture carbon and measure that, being able to grow seaweed and measure how well is that doing, being able to really find the minerals we need to build batteries faster, and etc. All of that is really, really what makes this project very special for me and the colleagues that are partnering with us for this.
So I know one of the things that people are probably going to ask about, we talk about the hydrothermal vents, the black smokers. I was trying to hunt down a photo from my trip, but we're looking at some of these moons, right? Enceladus Europa. is this the kind of thing that we could use on one of those moons? Is there a way to design this to add it to a mission to a different world?
Yeah, absolutely, Beth. And I think that's why NASA was the first agency to invest in this here, right? So here's what's going to happen, right? So you have Europa or Enceladus, our top priority planets or moons so far. And what you have is an ocean, right, that is essentially kept in place with a layer of ice, right, on top of it. So what's going to happen is we're going to land on the ice at some point. We'll drill or melt through the ice, and eventually we're going to hit the water, right? We're going to, touch water. And at that point, what do you do, right? At that point, you need to have a submersible submarine type of thing that can, on its own, because there's not going to be a human joystick in these things around in Jupiter or Saturn, you have to have an autonomous vehicle system that can explore the ocean around it on its own, right? And think about this: we've never been there. We're estimating what the ocean looks like, but we don't really know. And if planetary exploration has taught us one thing, is that the things that we know are very far from the things that we learn once we're able to touch down with a rover or with a lander, right? So, or humans on the moon, for that matter. So, if you think further in future, is we need to be able to have a system that can really quickly and very effectively, efficiently scan around, look around for chemicals, for traces of things that may be interested, and guide itself around, be an autonomous scientist on its own, right? So the technique that we use here that I mentioned earlier, right, the laser stuff that we're doing, that is the crux of the solution here, is that you are doing real-time analysis. You don't need to stop the vehicle, wait for analysis. You don't need to have a human joystick in this. The laser itself can adaptively tell the robot where to go, where not to go, what to do, what not to do. So the lessons learned from this mission that we have this coming week, and future missions that we have in the pipeline coming up in the next few months, is to really slowly bring autonomy to this system, to take me, myself, and my team out of the equation, so that we don't have to have scientists with PhDs or other degrees operating this, and just make this intelligence built into the system. So that is the technology progress that we're going to do in the next decades, really, until we're able to be ready to fly to Europa and drill and then eventually explore the oceans.
So I want to take some audience questions, and we do have some coming in. But first, will you please kind of tell everybody when and where this expedition is taking place, and for how long, and what you'll be doing on it?
Yeah, so we are going to be out at sea for 4 weeks, starting Monday. We're sailing off Honolulu in Hawaii, and we're going to be visiting the Kingsman Reef and the Palmyra Atolls, which are islands that are a couple of days cruise southwest from Hawaii. This expedition is managed by the Ocean Exploration Trust with funding from multiple agencies. And for about 4 weeks, we're going to be exploring places that we've never seen before. We're going to be exploring national monuments in the seafloor around these islands that the White House in particular hopes that we learn more so we can expand the monument to protect these areas better for future. I believe hopefully you, Beth, or somebody in the team can put a link to the expedition website, because you'll be able to see 24/7 for 4 weeks everything that's going on. Topside on the deck, we'll have cameras videoing and streaming in 4K everything that happens on the top in mission control, on the deck as the vehicle comes in and out, and everything that the vehicle is going to be seeing down in the bottom. Everything that we're going to be seeing in the mission control, you also will be able to see it 24/7 live streamed on the website here. So in case you guys cannot see the link in the chat here, just Google Nautilus Live if you are a fan of the deep sea, Captain Nemo, and the Jules Verne movie or book or before. Nautilus is the name of the vehicle of the vessel we're going to be. So nautiluslive.org is the place where you're going to see the stream of everything that's going to be happening.
And it looks like that link has been put in chat, so you guys can kind of hit on that one. If you are on LinkedIn or Twitter, you can find our press release, and that link is also in the press release as well. So check out those posts. All right, let's look at some of these questions. I'm gonna answer a quick question that was directed at me from Stephen, real quick. This is Hedy Lamarr. This way, I can do this. Okay, this is Hedy Lamarr. As was mentioned by someone else in the chat, she is known for not only being an actress in the golden days of Hollywood, but doing amazing research on frequency hopping during World War II to help with communications. And that frequency hopping technology actually led directly to the development of Bluetooth. So very amazing. This over here is some of the documentation from her patents for this technology. So that's who I keep in the background for some of these things. You know, an amazing woman. So thank you for asking about it. Let's see. Stephen also asked, what are the wavelengths of the lasers being used in these undersea experiments?
Yeah, so we're using green laser, 532 nanometers, and we're using 532 nanometers, to be precise. That's green. And that's similar to the essentially PowerPoint classroom lasers that professors use to teach. And we're also using ultraviolet laser at 356 nanometers. So we use both green and UV, 532 and 356.
Okay, that is good to know. Numbers are always great for people. Let's see. Oh, and Andy is asking, and we've already kind of talked about having you're doing this mission starting next week. Is there a mission that is set up beyond this to actually implement it? This is sort of a test mission. Is there further missions planned yet, or are you just still in the testing, make sure it works stage?
Yeah, so in fact, we are already building generation 2 of the system. So we are going to use this testbed, this first mission trial, to learn how things work, what things don't work, what can we improve, what we don't need anymore. So we'll use the input from these trials to upgrade the version 2 that we're already building. And the hope is that next spring, about a year from now, if not earlier, we will have an autonomous vehicle in which we will implement version 2, and we'll do the very first autonomous mission, essentially mowed alone somewhere, right, and start doing this mapping of the seafloor autonomously, with no cables and no humans in the loop. So I'm assuming, Beth, that we will do one of these again next time, and maybe
sure
we can.
We will.
You guys can check from time to time on our website and see the updates. But yeah, a year from now we're doing autonomy already.
Fantastic. It's moving so quickly now. Snowman's Apartment is asking, does it use an AI system? You had mentioned AI and machine learning. Is that already involved, or is that still to come?
Yeah, so it is already built into the system. In this case, we're limiting the use of AI to identifying the chemicals and the composition of the sample of the rocks, biology, and fluids that we want to analyze. And the reason for that is that twofold. One, we are getting 20 data points per second, right? So every second we shoot the laser 20 times, we get 20 responses. So no human is fast enough to analyze all of that. So we're using AI to filter through all the data and start making correlations of what we see with what our database, our training models have told the AI to interpret. So we have a little, if you want, a baby scientist already as an AI, right? So that is going to be able to do its first interpretation on the fly. We're going to monitor that very quickly and very carefully, because we want to make sure that, you know, in the next version we enhance this input, so that not only the system can passively identify compounds, but can actually tell the vehicle where to go, right? Think about this. You're going to be scanning quickly, and we're going to be seeing, you know, for the most part, maybe the same things. Once we find an anomaly, the AI in future will be able to flag it to tell the vehicle, hey, hold on, we're seeing something very exciting here. Go back, you know, change the pattern, you know, instead of a grid pattern, maybe do a spiral pattern, you know, or go back here and explore, spend more time, right? So yes, the answer is AI is fundamental to this mission. We'll test the very first version of that, like I said, just so far to classify, identify things like a scientist would do.
Okay, good. Great to know. Adam altogether is asking if you could explain fluorescence spectroscopy and what it can tell us.
Yeah, so quickly, so if you've been to a rock museum or a geology museum university, you probably have seen this experiment where you turn the lights on, then you turn it off, and you see rocks glowing in different colors, green, pink, blue, and all that. So that is fluorescence, right? So what happens in fluorescence is that a particular pigment, maybe in an algae or in a shell, will absorb our ultraviolet fluorescence, our ultraviolet light itself, and it will emit it back in different colors, this yellow, green, blue, pink that you've seen in the museum, right? So that's what fluorescence is. Fluorescence is light gets absorbed and it gets re-emitted at a very different wavelength, right? So what it tells us is in this particular mode that we're using, is telling us what the organic composition is, what the pigments are there. Do we have chlorophyll, carotenes, other pigments that give color to life, right? So that's the main goal of the fluorescence. Secondary goal is to look for rare earth elements. Part of the reason why these minerals in the museum glow crazy is because they have small amounts of rare earth elements. This could be the lanthanides and all the other exotic things in the periodic table. Remember your chemistry 101. All of that stuff are rare earths, but are very important for battery, solar panels, turbines, even for hydrogen storage and whatnot. So I think secondary goal of fluorescence is to look for these rare earth elements and potentially see if there is a particular enrichment of these rare earths in a particular area that we may be able to extract and to mine for advancing electrification faster than with just land minerals.
Fabulous. So a little bit of economic geology going on in there too.
Yep.
All right. So we've kind of reached the end. We've reached the end of our half an hour, and thank you, Pablo, for talking with us about this mission. I really highly recommend everybody go check out the live link when the mission starts. It's having been on one of these ships, getting to see what the cameras see is always very amazing. So if you can't come along on the cruise, you can come along on the cruise. And then we'll definitely have some social media coming out I'm going to see if I can capture some screen images and share those out too, so that people don't miss out on things. Thank you again for being here today with us and talking about this. I'm really excited because we talked when this was still sort of in development before we were even at this fantastic testing stage. So I'm really excited that you get to finally go test. I want to thank everybody for watching today, for asking questions. You guys have been great. And just as your weekly reminder, we are a 501c3 nonprofit organization. You guys are the ones that fund this fantastic outreach program where we get to bring our scientists to you and bring other science to you. So it's a great way for us to be able to share what's being done at the SETI Institute and with other science around the globe. So thank you, everybody, for being here. Thank you for all of the support that you give. If you are interested in contributing, you can go to SETI.org and click on the Give Now button. We also are happy to accept your bits, your subs, your super chats, and your Facebook stars. So all of these things go into the pot that allows us to bring you these kinds of programs. So thank you again, everybody, for watching us. Check out the podcast if you just want to sit and listen to us talk. That is also available, and come join us next time we have SETI Live happening. And Pablo, come back when you've got more stuff to tell us.
Thanks, Beth, and thanks everybody for tuning in today. Yeah, and keep your fingers crossed.